In our last video, we have studied different types of DC generators. So we have seen that mainly there are two types of generators, separately excited and self-excited. Then self-excited generators are further classified as DC shunt, DC series and DC compound generators. And there are two types of compound generators, short shunt and long shunt. Now we will solve few numerical problems on these different types of DC generators. Let us solve the first example. Now here a 4-pole DC generator means number of poles P is equal to 4 having 780 wave connected conductors means number of conductors Z is equal to 780, and as it is wave connected, number of parallel paths A is equal to 2, is running at 800 rpm. So speed n is equal to 800 rpm and delivering a load of 10 ohm means load resistance RL is equal to 10 ohm at the terminal voltage of 110 volt means terminal voltage V is 110 volt. The armature resistance is 0.5 ohm means Ra is equal to 0.5 ohm and shunt field resistance is 220 ohm. So RSH is equal to 220 ohm. Find armature current means we have to determine Ia. The induced EMF means Eg and the flux per pole, that is phi. These three quantities are to be determined. The brush voltage drop is 1 volt per brush. So total voltage drop in brushes V brush is equal to 2 volt because there are two brushes. So this is also shown here as it is a DC shunt generator. Field winding and armature are connected in parallel. So here load resistance is 10 ohm, voltage across load is 110 volt, then resistance of armature is 0.5 ohm and resistance of shunt field winding is 220 ohm. Now let us solve the problem. So first of all, load current IL. So current drawn by the load is equal to voltage across load divided by resistance of load. Now voltage across load is 110 volt and load resistance is 10 ohm. So IL is equal to 110 divided by 10, which is equal to 11 ampere. So current flowing through this load, it is equal to 11 ampere. Now we can calculate the field current. So field current ISH, field current through this winding ISH is V, that is the voltage across the winding, divided by RSH. So V is 110 and RSH is 220. So ISH is equal to 110 divided by 220, which is equal to 0.5 ampere. So current in this path, this ISH is equal to 0.5 ampere. Now we have to determine the armature current. Now this armature current is the sum of the field current and load current. So armature current IA is equal to IL plus ISH, which is equal to 11 plus 0.5, which is equal to 11.5 ampere. So this current IA, it is 11.5 ampere. Now this IA will produce voltage drop in armature, which is equal to IA into RA. In addition to that, there is brush voltage drop, that is V brush, and therefore Eg is equal to V plus IARA plus V brush. So substituting all these values, we will get Eg as 117.75 volt. So generated EMF is 117.75 volt. Now we have to determine the flux per pole. Now we know the expression for Eg, and Eg is given by, it is phi Pn upon 60 into Z upon A. So here we have to determine phi. We know number of poles as 4, N is 800 RPM, number of conductors are 780, then number of parallel paths are 2, and this Eg is equal to 117.75. So solving this, we will get the value of flux phi, and phi is equal to 0.0056 Weber. Let us solve the next example. A short shunt compound generator. So the type of generator is short shunt type. Supplies 200 ampere, means load current IL is 200 ampere. This current flowing through load, it is 200 ampere at 100 volt, means terminal voltage V is equal to 100 volt. This voltage is 100 volt. The resistance of armature, series field and shunt field is 0.04, means Ra is equal to 0.04. Armature resistance is 0.04. Then series field 0.03, RSE is equal to 0.03. So this resistance is 0.03, and shunt field winding resistance, resistance of shunt field winding RSH is equal to 50 ohm. Find the EMF generated, means we have to determine the generated EMF Eg. Now, first of all, let us calculate the voltage drop in this series field winding. The current in this series field winding is the load current IL, and its resistance is RSE, and therefore voltage drop in series field winding is IL into RSE. So voltage drop in series field winding is load current IL 200 into RSE. RSE is 0.03, and therefore voltage drop in series field winding is equal to 6 volt. So here the drop is 6 volt. Now we have to calculate the shunt field winding current ISH. Now ISH is equal to the voltage across the shunt field winding. Let us call it as V dash divided by RSH. So shunt field winding current ISH is equal to V dash upon RSH. This V dash is equal to voltage V plus voltage drop in series field winding. Therefore, V dash is equal to 100 plus 6, that is 106. So V dash is equal to terminal voltage V plus voltage drop in series field winding, which is equal to 106 volt. And therefore, voltage across shunt field winding is 106 volt. Now current through this winding, shunt field winding, ISH, it is V dash upon RSH. So it is 106 upon 50, which is equal to 2.12 ampere. So ISH is equal to 2.12 ampere. Now current IA is the sum of load current IL and shunt field winding current ISH, and therefore armature current IA is equal to IL plus ISH, which is equal to 200 plus 2.12, which is 202.12 ampere. So current in armature IA, it is 202.12 ampere. Now we can determine the generated EMF EG. Now EG is equal to terminal voltage V plus voltage drop in armature, which is equal to IA into RA, plus voltage drop in series field winding, which is equal to IL into RSE, plus brush contact voltage drop V brush. So EG is equal to V plus IARA plus ILRSE plus V brush. So substituting all the values, it is equal to 114.08 volt. V brush here, it is not given, so it is assumed as 0. So generated EMF EG is equal to 114.08 volt. Let us solve next example, which is on long shunt type compound generator. In a long shunt compound generator, the terminal voltage is 230 volt. So V is equal to 230 volt. When generator delivers 150 ampere, so IL is equal to 150 ampere. Determine induced EMF, means we have to determine EG, and total power generated. Total power generated in armature is Eg into Ia. So that we have to calculate. Given that shunt field, series field diverter and armature resistance are 92, means shunt field resistance RSH is equal to 92 ohm. Series field resistance RSE is equal to 0.015 ohm. Series field diverter is 0.03 ohm. So RD is 0.03 ohm and armature resistance RA is equal to 0.035 ohm. So series field diverter, this resistance RD, it is connected in parallel with the series field winding, so that some armature current can be diverted through the diverter, and that current will not flow through the series field winding. So in this case, current in series field winding ISE is not equal to IA, because some current is diverted through this RD. Now let us first of all calculate the current in shunt field winding. Now the voltage across shunt field winding is terminal voltage V, and therefore ISH is equal to V upon RSH. So it is equal to 230 upon 92, which is equal to 2.5 ampere. So current in this winding is 2.5 ampere. Now we can calculate the armature current. Now current through armature IA is equal to ISH plus IL. So IA is equal to IL plus ISH, which is equal to 150 plus 2.5, which is equal to 152.5 ampere. So current here in this branch, it is 152.5 ampere. Now RSE and RD are connected in parallel, and therefore equivalent resistance of RSE and RD connected in parallel can be calculated. So the equivalent resistance of the combination is RSE into RD upon RSE plus RD. So it is equal to 0.01 ohm. So the combined resistance of this combination is 0.01 ohm, and resistance of armature, it is 0.035 ohm. So we can calculate the combined resistance of this series path, which is the resistance of armature Ra plus equivalent resistance of this series combination, and therefore total armature circuit resistance means total resistance of this path, it is equal to 0.01, which is the resistance of combination, plus 0.035, which is the resistance of armature, and therefore total armature circuit resistance, it is 0.045 ohm. Now we can calculate the induced EMF Eg. So Eg is equal to V plus Ia into the total resistance of armature path, and therefore Eg is equal to V plus Ia into effective resistance of armature circuit. So it is calculated as 0.045, and current through this path, it is the armature current, which is 152.5, and therefore Eg is equal to 236.86 volt. So EMF generated is 236.86 volt. Now the total power developed, it is equal to Eg into Ia. So total power generated in armature, it is Eg into Ia, which is equal to 36121.15 watt. Let us solve the next problem. A long shunt compound generator has 1200 shunt field turns, means number of shunt turns per pole, it is 1200, and 5 series turns per pole, means number of series turns per pole, it is equal to 5. So these turns are 1200 and these turns are 5. The resistance of series field winding is 0.045 ohm, means RSE is equal to 0.045 ohm. If the machine is used as a shunt generator, means if this machine is used as shunt generator, then RSC and RD will not be there. It is used as a shunt generator. Then to obtain the rated voltage at full load, it is essential to increase the field current by 0.25 ampere. In case of DC shunt generator, when the generator is loaded, its terminal voltage decreases. Now if we want same voltage at full load, we have to increase the shunt field ampere turns. Now these shunt field ampere turns can be increased by circulating additional current in the shunt field winding. Now in this case, this additional current in the shunt field winding required is 0.25 ampere. The full load armature current is 100 ampere, means Ia at full load is equal to 100 ampere. So this current, it is 100 ampere. Find the diverter resistance connected in parallel to series field, means we have to find Rd to obtain flat compound operation, means to obtain constant terminal voltage. So we have to calculate the resistance of diverter Rd such that in case of long shunt generator, we will get the constant voltage at no load and at full load. So here, first of all, when the machine is used as shunt generator, then additional current of 0.25 ampere is required, and that additional current is flowing through shunt field turns of 1200. So additional ampere turn by the shunt field winding. Ampere turn is the product of current in ampere multiplied by number of turns, and therefore additional ampere turns to obtain constant voltage. If the machine is used as a shunt generator, then it is equal to additional current, that is 0.25, multiplied by number of turns of shunt field winding, which is 1200, and therefore additional ampere turn, it is equal to 300. So this winding should produce additional 300 ampere turns so that terminal voltage will remain constant at full load. Now, if we are using long shunt compound generator, then these additional 300 ampere turns must be produced by series field winding. Then the constant terminal voltage can be obtained, and therefore the additional ampere turns produced by series field winding, it is 300 ampere turn, and number of series field winding turns, it is equal to 5, and therefore the current required to produce additional 300 ampere turns by series field winding, it is equal to 300, that is additional ampere turns required, divided by 5. 5 is the number of turns of series field winding. So it is equal to 300 upon 5 is equal to 60 ampere. Means if we want constant terminal voltage, current through series field winding must be equal to 60 ampere. But the armature current is 100 ampere. If diverter is not there, then ISE is equal to IA, and in that case current through series field winding will be equal to 100 ampere and not 60 ampere, and therefore here a diverter is connected to divert the remaining current. So here total current is 100 ampere, and current in series field winding must be 60 ampere, and therefore current in diverter must be equal to 100 minus 60, that is 40 ampere, and therefore current in diverter must be equal to 100 minus 60, that is 40 ampere. So here in this path current must be 40 ampere, and in this path current must be 60 ampere. Now here 60 into RSE must be equal to 40 into RD, and using this we can calculate RD. So ISE into RSE must be equal to ID into RD. Here ISE is 60 and RSE is 0.045 ohm, and therefore RD is equal to ISE into RSE upon ID, and ID is 40 ampere, and therefore RD is equal to 0.0675 ohm. Means if the value of RD is equal to 0.0675 ohm, then at full load it will divert a current of 40 ampere, and therefore current through series field winding will be equal to 60 ampere, and this series field winding will produce ampere turns which are equal to 300, and because of these 300 ampere turns, this voltage will remain constant, and we will get same voltage at no load and at full load. And this type of compound generator, it is called as flat compounded generator. So to obtain flat compounded operation, RD must be equal to 0.0675 ohm. Thank you. Stay home, stay safe.